3I Atlas is dangerously close to the Sun right now. This third ever confirmed interstellar object is tearing through the inner solar system, crossing inside the orbit of Mars and hurtling toward its closest approach at nearly 68 kilometers per second. But precisely when the world's telescopes fall blind during a mid-October solar conjunction, Atlas will plunge into the Sun's intense electromagnetic field, vanishing from Earth's view. Every scientist is left with nothing but speculation and mounting questions about its bizarre chemistry, enormous scale, and unpredictable nature. What happens when a possible 50-kilometer object from another star system collides with a solar wind at maximum velocity, invisible to all human observation? The timeline, the dangers, and the unsolved mysteries all converge at this moment. Currently, this cosmic wonder carves its own trajectory inside Mars's orbit, tilted roughly 5 degrees off the ecliptic, a path so steep and retrograde that it slices almost head-on through the plane of the solar system. The orbital inclination measures 175 degrees, a figure that emphasizes just how alien its origins truly are. Most comets and asteroids travel in the same general direction as the planets, but this one is a genuine outsider, approaching from the opposite direction and crossing the planetary highway at an aggressive angle. The numbers alone paint a picture of relentless acceleration. When first detected by the Atlas survey in early July, its velocity already reached an impressive 58 kilometers per second. Now, as it plunges deeper toward the Sun, that speed climbs steadily, projected to hit nearly 68 kilometers per second at perihelion. Imagine that for a moment, a chunk of interstellar debris, possibly as wide as a medium-sized city, screaming through the solar system faster than any spacecraft humanity has ever built. At this rate, it covers the distance from Earth to the Moon in just over an hour. Perihelion arrives on October 29th at 11:55 Universal Time Coordinated. The closest approach to the Sun will occur at approximately 1.36 to 1.40 astronomical units, just inside Mars's orbit, yet still well beyond Earth's own path. Unlike the sun grazers that flirt with destruction, this visitor won't dive into the solar corona. Instead, it skirts the boundary of the inner system, threading through the region where solar wind and electromagnetic fields reach their most turbulent state. The geometry places it in the constellation Virgo at closest approach, but from Earth's perspective, the Sun's glare renders it completely invisible. The orbital elements catalogued by the Minor Planet Center confirm a hyperbolic trajectory, an eccentricity greater than 1. This mathematical signature guarantees it will never return. Its inbound track, outbound escape, and the sharpness of its solar swing all point to a brief, one-time passage. Every kilometer it travels now brings it closer to the Sun's domain, and farther from the only vantage points capable of tracking its journey. This is a geometry of a cosmic interloper. Inside Mars, 5 degrees off the ecliptic, accelerating from 58 to nearly 68 kilometers per second, with a rendezvous with the Sun scheduled for October 29th. The numbers are precise, the timeline is fixed, and the window for direct observation is closing with every passing hour. From Earth's vantage point, the calendar becomes stark. October 21st, 2025 brings Superior Conjunction, the moment when 3I Atlas slips directly behind the Sun, hidden from every ground-based telescope and even most space observatories. For the next several weeks, solar glare dominates the sky, drowning out any trace of this interstellar visitor. Astronomers call it a blackhead and enforce silence when no new data can be gathered, regardless of how advanced the equipment. The Sun's disk acts as a blinding curtain, blocking not only visible light but also most infrared and ultraviolet signals. Picture the frustration. After months of urgent coordination, over 120 observing runs, emergency override programs at flagship telescopes, frantic Slack channels, and late-night Zoom calls, the entire global campaign is forced into silence. The geometry is unforgiving. Solar elongation, the angle between the comet and the Sun as seen from Earth, shrinks to nearly zero. Even the most ambitious adaptive optics or twilight observation attempts fail. Detectors face damage risk, and safety protocols trigger automatic shutdowns. The last reliable data points trickle in around October 18th, as the object apparent separation from the Sun dips below critical thresholds. Coronagraphs, those specialized solar observatories designed to block the Sun's blinding core, offer little hope. At magnitude 12, 3I Atlas is simply too faint and too compact to stand out against the turbulent brightness of the corona. Deep background subtraction and image stacking techniques so effective for brighter sun grazers fall short here. No confirmed detections have emerged from SOHO, Stereo, Parker Solar Probe, or Solar Orbiter during this window. Attention briefly turns to Mars. In early October, orbiters like Mars Express and the ExoMars Trace Gas Orbiter captured a handful of long-exposure images and low-resolution spectra as the comet skimmed past the red planet. Their vantage point offered a fleeting advantage, one last glimpse before the sun intervened. Yet even these datasets are limited. The coma appears as a faint, fuzzy dot. The nucleus remains unresolved, the tail invisible to their sensors. Attempt to redirect Mars orbiters for perihelion phase imaging sparked debate within mission teams. Resource constraints, orbital geometry, and instrument safety ultimately prevailed. The opportunity closed. So when does a silence break? The recovery window opens in mid to late November as 3i Atlas emerges from behind the sun and reclaims position in the dawn sky. By then, it will be receding both in distance and brightness, but still within reach of large telescopes and dedicated amateur astronomers. The calendar's next milestone, December 19th, 2025, when the comet makes its closest approach to Earth at about 1.80 astronomical units, just before the winter solstice. Between conjunction and reacquisition, the narrative is one of anticipation and uncertainty. Every hour lost to the sun's glare is an hour when the most anomalous interstellar object ever recorded could transform, fragment, or simply fade away unseen. The scientific clock is ticking, and the world waits for the first signal to break through the solar curtain. Size, in this case, refuses to settle into a single definitive number. Early photometric readings drawn from dozens of telescopes across both hemispheres suggested a nucleus somewhere between 5 and 50 kilometers wide, potentially the largest interstellar object ever observed. That range isn't a rounding error. It's a symptom of an object shrouded in its own activity. The coma, a diffuse envelope of gas and dust, expands so densely around the core that even the most powerful ground-based mirrors and Mars-orbiting cameras cannot resolve the true solid body. Instead, astronomers must infer mass and volume from indirect clues: how the object brightens, how its light scatters, how quickly the coma thickens as it approaches the sun. Color also tells a story of transformation. Through June and July, the coma spectrum leaned red, perhaps an indicator of complex organic grains or larger, slowly sublimating particles. By August, something changed dramatically. The coma shifted to a pronounced green, a hue rarely seen so intensely in solar system comets. Spectroscopic campaigns, including those with the Canada-France-Hawaii Telescope and the James Clerk Maxwell Telescope, tracked this evolution in real time. The culprit appears to be an upsurge in carbon-based molecules, especially C2 and CN radicals, unleashed as the comet's CO2 content vaporized under mounting solar heat. The green glow isn't just a visual oddity, it's a chemical fingerprint, revealing that carbon dioxide, not water, dominates the outgassing. That alone sets 3i Atlas apart from most known comets, whose activity is typically driven by water ice. The chemical portrait grows stranger still. Spectra obtained from both hemispheres and embargoed preprints circulating among specialist teams point toward a nickel-to-iron ratio far outside typical solar system bounds. Nickel lines, strong and persistent, outshine their iron counterparts by margins that hint at an origin in a supernova remnant or the stripped core of an ancient differentiated planet. If confirmed, this would rewrite assumptions about what kinds of debris survive the interstellar journey. The dust itself, as revealed by polarimetric studies, shows extreme negative polarization. Light scatters in a way that betrays preponderance of fine, possibly glossy or metallic grains rather than the silicate-rich material familiar from local comets. Morphology presents yet another puzzle. Instead of a classic antisolar tail, 3i Atlas sports a coma that is brightest on the sunward side, with a forward-scattering envelope that defies standard models of dust and gas flow. The sun-facing edge gleams with a density and texture that has prompted heated debate among observers. Some argue for a jetting phenomenon. Others propose a sheet of highly reflective metal-rich dust. The antisolar tail, if present, remains faint and elusive, a mere whisper against the glare. The light curve, tracked obsessively in the weeks before solar conjunction, adds urgency to the mystery. Instead of fading as expected, the comet's brightness climbed steadily even as it crossed Mars's orbit and entered the sun's domain. This pre-gap brightening, recorded in the final days before data blackout, fueled a storm of speculation across every observer channel. Was it a sign of fragmentation, a new outburst of volatile gas, or simply the unveiling of fresh surface layers never before touched by sunlight? Each anomaly, size, color, chemistry, polarization, Comet geometry, has drawn the attention of a sprawling, loosely coordinated observer community. Professional astronomers, amateur sky watchers, planetary scientists, and instrument specialists have converged in digital forums, racing to decipher the object's secrets before technical limits and the sun's glare imposed silence. Their findings, arguments, and unanswered questions now set the stage for a deeper confrontation with the limits of our instruments and the boundaries of current cometary science. Magnitude 12, that's a predicted brightness of 3I Atlas as it sweeps behind the sun. Fainter than any planet, far below the detection threshold of most solar observatories. For instrument engineers and data analysts, that single number defines a practical boundary between wishful thinking and genuine measurement. Coronagraphs like SOHO's LASCO C3 or Stereo's heliospheric imager are built to block the sun's glare and reveal dramatic outbursts, but their detectors are tuned for objects at least 100 times brighter than this interstellar visitor. Even with heroic digital processing, the surface brightness of the Comet falls short. The comet's angular size, just a few arcseconds at best, renders it indistinguishable from the background noise of the solar corona. No confirmed detections have surfaced from any solar-focused spacecraft, not from SOHO, not from Stereo, not from Parker Solar Probe, not from Solar Orbiter. The standard data products, those daily movies of the inner solar system, show nothing but turbulent plasma and the occasional planet. For 3I Atlas, the signal-to-noise ratio remains stubbornly below 1, even when stacking dozens or hundreds of images. The Comet's faint, diffuse glow is simply overwhelmed by the ever-changing light patterns that surround the sun. Some teams propose a workaround, shift and stack. The concept is elegant in theory. Take hundreds of images, predict the comet's apparent motion across a detector, and digitally align each frame so that any faint moving object accumulates signal while static background features cancel out. On paper, this method can push the detection limit down by a full magnitude or two. In practice, it demands an accurate ephemeris, precise knowledge of the comet's path, and a willingness to wade through terabytes of noisy data in search of a single faint smudge. For 3I Atlas, even the most optimistic shift-and-stack campaigns, 100 frames from LASCO, 50 from Stereo, still fall short of a secure detection. The mathematics are unforgiving. The expected gain in signal-to-noise is swamped by the sheer faintness and compactness of the Comet. Instrument safety protocols introduce another barrier. As the comet's solar elongation drops below critical angles, automatic shutdowns activate to protect sensitive detectors from accidental exposure to the sun's disk. No amount of manual override can justify risking a billion-dollar imager for a target that may not even be visible. For ground-based telescopes, the situation is even more stark. The sun's glare saturates the sky, and no amount of adaptive optics or horizon skimming can extract the comet from the haze. Mars orbiters offered a brief glimmer of hope. Their unique vantage point allowed for a handful of long-exposure images in early October. But by the time perihelion arrived, their orbital geometry and instrument constraints closed that window. No high-end telescope on Earth, in orbit, or circling Mars remained in position to watch the critical moment when solar heating peaked. For now, the data gap is absolute. The world's best coronagraphs and heliophysics images are forced to admit defeat. 3I Atlas is simply too dim, too small, and too close to the sun for any direct measurement during conjunction. The only path forward lies in creative data mining, reprocessing old exposures, stacking images along predicted tracks, and hoping for a post-conjunction surprise. Instrument teams are already sketching out contingency plans for future interstellar visitors, more flexible safing protocols, dedicated shift-and-stack pipelines, and perhaps one day, solar observatories designed specifically to chase faint comets through the glare. For now, the boundaries are clear. The object is out there, racing unseen, and the instruments built to catch it have met their match. The moment 3I Atlas swings closest to the sun, a new set of questions comes into sharp focus, questions that stretch beyond standard cometary models. Among the most vocal are advocates for electromagnetic explanations, the so-called electric universe theorists who argue that comets are not merely icy relics but dynamic players in the solar plasma environment. For them, perihelion is more than a gravitational checkpoint. It's a natural laboratory where solar wind, electric fields, and charged dust could interact in ways that leave measurable fingerprints. One hypothesis on the table: a sudden outburst of activity triggered not by heat alone, but by the object's plunge through regions of intense electromagnetic flux. If the comet's carbon dioxide-rich dust is electrically charged, the sun's field could accelerate particles, alter the comet's shape, or even shift the trajectory by a detectable margin, effects that would show up as small but real deviations in post-perihelion tracking. Dusty plasma specialists are already drafting diagnostic metrics: changes in coma polarization, unexpected drifts in the outbound path, or a burst of radio emission as solar wind slams into a dense metal-rich envelope. No one is claiming certainty. These are testable predictions, not declarations. When 3I Atlas reappears in November, every new data point, brightness, position, coma structure, will serve as a diagnostic for mission planners and alternative theorists alike. The next phase is a waiting game, with the hope that nature might deliver a verdict on ideas long considered fringe. Astrologers tracking the sky at perihelion note a rare convergence. As 3I Atlas threads through the constellation Virgo, it stands in direct opposition to Chiron with Eris nearby, while Jupiter and Pluto form their own axis across the heavens. Chart watchers read these alignments as a grand cross overlaid with kite and grand trine motifs that have long been associated with crisis, transformation, and the search for deeper purpose. Some interpret the comet's passage through Virgo as a symbol of healing through disruption, a reminder that even the most alien visitor can stir ancient patterns of reflection and renewal. For those who follow planetary cycles, the timing resonates. 3I Atlas makes its closest pass by Earth just before the winter solstice, a season marked by darkness turning toward light. The outbound journey brings the traveler into a close encounter with Jupiter by March, a progression that in astrological tradition hints at the possibility of new beginnings and shifting collective priorities. Whether these patterns are read as cosmic metaphor or simple coincidence, they offer a bridge between scientific observation and human meaning-making. For viewers who want to mark the occasion, commemorative designs are available. The story of 3I Atlas continues, woven from both data and dreams. As the world waits for its return to view, key questions persist. What drives its anomalous behavior? Will perihelion trigger changes in activity or trajectory? These answers await its reappearance in mid to late November. As the data gap continues, each new observation of 3I Atlas will test our understanding of interstellar visitors and the limits of solar system science. For now, only the archival record stands, a reminder of how much remains hidden, even as the evidence grows. The cosmic wonder races on through the solar furnace, carrying secrets that may reshape our understanding of what travels between the stars and what happens when those travelers pass through our celestial neighborhood at breakneck speed, shrouded in the sun's blinding light. November 14th, 2025, 3:42 Universal Time Coordinated. A grad student of the European Southern Observatory's La Silla facility in Chile catches at first a faint smudge in the dawn sky, exactly where the ephemeris predicted 3I Atlas should emerge. Within minutes, confirmation pings arrive from Hawaii, Japan, and South Africa. The interstellar visitor has survived, but something is catastrophically wrong. The brightness readings don't match. Instead of the expected magnitude 13 post-perihelion fade, the object blazes at magnitude 9, nearly 16 times brighter than predicted. Slack channels explode. Emergency observing requests flood every major telescope queue. By sunrise, 36 facilities have pivoted their instruments toward Virgo. Dr. Sarah Chen at Gemini North captures the first high-resolution image at 5:17 Universal Time Coordinated. Her hands shake as the data resolves on screen. The coma has transformed into something unprecedented, a brilliant emerald shroud extending over 400,000 kilometers, pulsing with internal structure. Jet-like features spiral outward in a pattern that defies every dust fountain model in the literature. It's fragmenting, she whispers into the Zoom call, her voice cutting through 24 simultaneous conversations. No, wait! It's not fragmenting. It's shedding. Over the next 72 hours, the Global Observer Network documents an event without parallel in astronomical history. 3I Atlas isn't dying, it's undergoing a violent transformation. Spectroscopic data from Keck in the Very Large Telescope reveals the chemistry has shifted again. The carbon dioxide signature that dominated pre-perihelion observations has nearly vanished, replaced by emission lines that shouldn't exist. Exotic ionization states of nickel and chromium, molecular species never before detected in cometary spectra, and a persistent, inexplicable infrared excess centered at 3.4 microns. Dr. Marcus Webb, analyzing the VLT data from his office in Munich at 2 a.m., goes rigid in his chair. That 3.4 micron signature. He's seen it before, in the spectra of complex organic molecules, in the emission from protoplanetary disks, in the theoretical predictions for carbon-based polymers formed in the cold of interstellar space. It's not a comet, he types into the group chat, fingers flying across the keyboard. It never was. The perihelion heating didn't destroy the nucleus, it activated something inside it. November 18th brings the breakthrough. Mars Express, in a fortuitous orbital alignment, captures a series of thermal infrared images as 3I Atlas passes 0 Australian dollars and 80 cents from the red planet. The resolution is marginal, barely sufficient, but it's enough. The nucleus is intact, roughly 47 kilometers across, confirming the high end of initial estimates. But the surface temperature readings are impossible. The sunward hemisphere should be radiating waste heat from perihelion solar bombardment. Instead, it's significantly cooler than the night side. The object is somehow absorbing solar energy without the expected thermal response. Dr. Yuki Tanaka, a planetary scientist specializing in asteroid thermal inertia, runs the numbers 3 times before calling an emergency meeting of the project leads. Either our models are completely wrong, she explains, pulling up side-by-side thermal maps, or this object has internal heat sources compensating for solar input. The temperature inversion is, it's not natural. Define natural, someone challenges from the back of the virtual room. I mean, it's not consistent with a passive body under solar illumination. Something inside is generating heat, or redistributing it. Oh! She trails off, staring at the anomaly map where the nucleus should be a simple hot-cold gradient, but instead shows a complex pattern of thermal cells. November 22nd. The Minor Planet Center issues an urgent circular. 3I Atlas's post-perihelion trajectory doesn't match predictions. The deviation is small, just 0.3 arcsecond on the sky, but statistically significant and growing. Non-gravitational forces. Every comet experiences them as outgassing jets provide tiny thrusts, nudging the orbit in unpredictable ways. But this is different. The magnitude of the acceleration is an order of magnitude larger than the observed outgassing can account for. And the direction is wrong, perpendicular to both the Sun-Comet line and the expected jet thrust vectors. Dr. Anatoly Volkov, a celestial mechanician who has spent 30 years calculating comet orbits, pulls data from 60 tracking stations worldwide and feeds it into the most sophisticated trajectory software available. The solution that emerges makes him lean back from his screen, removing his glasses to rub his eyes. It's accelerating, he announces in the daily coordination meeting, his Russian accent thick with exhaustion. Not decelerating as it should, leaving perihelion. Something is pushing it, the magnitude suggests. He pauses, checking his numbers again. If this were a spacecraft, we'd call it a 0.02 millig continuous thrust. For a 50-kilometer object, that requires impossible amount of energy, someone finishes. By December, 3I Atlas have become the most observed object in the solar system. Every professional observatory, every major amateur astronomer, and half the world's physics graduate students are pointing instruments toward Virgo, then Libra, then Scorpius as the object traces its hyperbolic arc. The light curve remains stubbornly bright. The coma continues to pulse and restructure. The spectroscopic anomalies multiply, and the trajectory deviation continues to grow, suggesting the object is somehow steering itself. The electromagnetic universe theorists are vindicated, partially. Magnetometer data from scattered spacecraft show unusual perturbations in the interplanetary magnetic field as 3I Atlas passes. Not proof of their most radical claims, but something measurable, something real. The plasma interactions are stronger than predicted. The comet is electrically active in ways solar system comets never are. March 2026 brings a final act of the drama, the Jupiter flyby. 3I Atlas sweeps past a giant planet at $0.40, close enough for Jupiter's gravity to bend its outbound path, but not enough to capture it. The encounter is brief, lasting less than a week in Jupiter's gravitational sphere of influence. But in that week, something extraordinary happens. The Hubble Space Telescope, granted emergency override time, captures it in exquisite detail. As 3I Atlas enters Jupiter's magnetosphere, that vast bubble of charged particles and magnetic field lines, the coma explodes, not in brightness, but in structure. Filaments of glowing gas extend millions of kilometers, following magnetic field lines like iron filings around a magnet. And for 6 hours on March 15th, as the comet reaches its closest approach to Jupiter, radio telescopes across Earth detect something that will be debated for decades, a series of electromagnetic pulses, rhythmic and structured, emanating from the vicinity of 3I Atlas. 19 pulses, each lasting 1.7 seconds, separated by exactly 31 seconds of silence. Natural phenomena, plasma instabilities, or something else. By June 2026, 3I Atlas is receding beyond Saturn's orbit, fading back toward the threshold of detectability. It will cross Neptune's orbit in 2029, pass the heliopause sometime in the 2040s, and return to the interstellar void from which it came. Behind it, the object leaves a transformed scientific landscape. Over 400 papers are published in its wake. 3 competing models attempt to explain the thermal anomalies. 5 different research groups claim to have decoded the Jupiter radio signal, each reaching different conclusions. The electromagnetic comet theory gains respectful attention, if not universal acceptance. Most significantly, planetary defense protocols are quietly revised. The working group discussions are classified, but the conclusions leak. If an interstellar object can accelerate itself, if it can withstand perihelion passage and emerge transformed rather than destroyed, if it can interact with planetary magnetospheres in unpredictable ways, then humanity's assumptions about what might arrive from the stars require fundamental reconsideration. Dr. Sarah Chen, the grad student who captured that first post-perihelion image, finishes a doctoral thesis on the 3I Atlas observations. The final paragraph reads, "We detected 3I Atlas as an icy intruder, tracked it as an anomalous comet, and watched it depart as something we still cannot fully categorize. Whether it was a fragment of an ancient planetary core, a pristine sample of interstellar matter transformed by stellar passage, or something more exotic, we may never know with certainty. What we learned is humbling. The universe sends us messengers we are barely equipped to read, carrying information in languages we are only beginning to decipher. The next interstellar visitor may arrive in 5 years or 500. When it does, we will be watching, with better instruments, deeper questions, and the hard-won knowledge that our solar system is not an isolated island, but a crossroads where travelers from distant shores pass through, leaving ripples in their wake." December 2027. A preprint appears on the ARCS server at 3 a.m. Greenwich Mean Time. The author list includes 57 names from 23 institutions. The title, Differential Analysis of 3I Atlas Surface Thermal Patterns, Evidence for Subsurface Voids and Possible Internal Structure. The abstract is clinical, but the implications ripple through the community within hours. Using every thermal observation from the entire flyby period, the team has reconstructed a 3-dimensional heat map of the nucleus. The conclusion: the object is not solid. The thermal signature suggests complex internal architecture, voids, chambers, or possibly even a differentiated structure with a dense core and less dense outer layers. One of the supplementary figures, buried on page 47 of the supporting materials, shows a geometric pattern in the subsurface void distribution. It's tentative, possibly an artifact of the reconstruction algorithm. But it's there, a hexagonal lattice, too regular to be entirely random, repeating across multiple spatial scales. The paper's final sentence reads, "Further observations of future interstellar objects, particularly with dedicated deep space missions, will be required to determine whether such structural features are common in extrasolar material or unique to this object." But in the private Slack channel where the core research team communicates, the conversation is less circumspect. So are we going to talk about figure S47? Not until we've checked it 50 more ways. I've checked it. It's real. Real doesn't mean what you think it means. Then what does it mean? 50 kilometers across. Internal structure. Self-acceleration. Radio pulses. And now geometry. A long pause in the chat. It means someone finally types. We write the paper very carefully. We present the data. We let others draw conclusions. And we start building the kind of mission that could actually intercept the next one. If there's a next one. Oh, there will be. If 3I, our atlas, taught us anything, it's that interstellar space is more crowded than we thought. And whatever's out there between the stars, natural, artificial, or something in between, it's been traveling for a very long time. The chat falls silent. Outside their windows, scattered across multiple continents, dawn is breaking. And somewhere beyond Neptune, beyond Pluto, beyond the edge of the solar system's gravitational embrace, 3I Our Atlas continues its journey into the eternal night between stars, carrying secrets that humanity glimpsed but could not grasp, and questions that will haunt a generation of astronomers waiting for the next messenger from the cosmic dark. The wait has already begun.